In 1972, while America was celebrating the success of Apollo 16 and preparing for the final moon landing, NASA quietly shut down an ambitious artificial intelligence project that had consumed millions in funding and thousands of engineering hours. This wasn't just another canceled government program, it was a decisive rejection of what many believed was the future of space exploration. And yet, today, NASA has become one of the world's leading AI innovators. What happened? This AI initiative, codenamed DSKY-AI, was designed to give spacecraft computers the ability to make autonomous decisions during critical mission phases. With astronauts' lives and billion-dollar equipment at stake, NASA invested the equivalent of $78 million in today's dollars to develop systems that could think and adapt during the most dangerous moments of spaceflight. Engineers believed this technology would be essential for deep space missions where communication delays made Earth-based control impossible. Stay with me until the end to learn the 3 revolutionary approaches NASA developed instead of AI, because these same principles are quietly reshaping today's most advanced technologies while most experts are looking elsewhere. The story begins in 1968 during the height of Apollo program development. NASA engineers faced a fundamental problem: how to manage the incredible complexity of lunar missions when communications with Earth could be interrupted, and astronauts were busy with numerous tasks. The Apollo guidance computer, though revolutionary for its time, followed only pre-programmed instructions and couldn't adapt to unexpected situations. A special team was assembled at the Instrumentation Laboratory, now Draper Laboratory, at MIT, working alongside the main Apollo guidance team. Their mission: develop a system that could make intelligent decisions without human intervention. The project was called DSKY-AI, named after the display and keyboard interface DSKY that astronauts used to communicate with the Apollo guidance computer. The team's vision was revolutionary for the time. They aimed to create software that could analyze sensor data, identify anomalies, make decisions based on incomplete information, and even learn from experience. These capabilities would be crucial for future missions to Mars and beyond, where communication delays would make Earth-based control impractical. Initial results were promising. By 1970, the team had developed rudimentary systems that could handle simple anomalies in simulated environments. NASA leadership was impressed enough to increase funding, believing this technology would be essential for the post-Apollo era. The DSKY-AI system was scheduled to fly its first demonstration mission on Apollo 19. But here's where the story takes an unexpected turn. As you might know, Apollo 18, 19, and 20 were canceled due to budget cuts. With the end of the Apollo program, the DSKY-AI team needed to demonstrate immediate value to secure continued funding. In a critical 1972 test, the system was connected to a lunar module simulator to demonstrate autonomous landing capabilities. What happened next sealed the project's fate. During the simulation, the AI system encountered an unusual sensor reading and made a decision that would have crashed the lunar module. While the developers argued this was a simple bug that could be fixed, NASA leadership saw something far more concerning: inherent unpredictability. Gene Kranz, the legendary flight director who had guided the Apollo 13 crew home, witnessed the test and delivered the verdict that ended the project. "I don't want a computer that thinks. I want a computer that knows." This seemingly simple statement revealed a profound insight about the nature of mission-critical systems that remains relevant today. NASA didn't abandon AI because it didn't work. And in spaceflight, that unpredictability was unacceptable. Following the cancellation of DSKY-AI, NASA's approach to spacecraft autonomy took a radically different direction. Instead of pursuing systems that could think independently, they developed 3 alternative approaches that would prove far more successful. The first was fault protection systems, specialized software designed not to make independent decisions, but to recognize specific error conditions and respond with predetermined actions. Unlike AI systems that might devise novel responses to problems, fault protection followed exhaustively tested logic paths that engineers could verify with mathematical certainty. These systems made their debut on the Viking Mars landers in 1976. During descent to the Martian surface, Viking 1 encountered wind conditions that threatened to destabilize the lander. The fault protection system detected the anomaly and adjusted the descent thrusters precisely as designed, resulting in a successful landing. This wasn't intelligence, it was engineering precision. The second approach was redundancy and voting systems. Instead of one smart system, NASA used multiple simple systems that performed the same calculations independently and voted on the correct action. If one system produced a different result, it was overruled by the others. This approach was dramatically demonstrated during the Space Shuttle program. On STS-9 in 1983, one of the shuttle's 5 general-purpose computers failed during re-entry, producing erroneous commands that could have been catastrophic. The voting system immediately recognized the discrepancy, ignored the failed computer, and continued the landing sequence flawlessly using the remaining computers. The third alternative was human-computer teaming, carefully dividing responsibilities between automated systems and human operators based on their respective strengths. Computers handled precise calculations and rapid response tasks, while humans managed uncertainty and judgment calls. This approach proved its value during the Hubble Space Telescope servicing missions. The computer systems handled the precise orbital mechanics and stabilization, while astronauts performed the delicate repair work that required adaptability and real-time judgment. Neither could have succeeded alone. What's fascinating is that these 3 approaches, fault protection, redundancy with voting, and human-computer teaming, remain the foundation of NASA's approach to spacecraft autonomy today, even as they've begun to selectively incorporate modern AI technologies. The Mars rovers provide a perfect example of this evolution. When the Spirit and Opportunity rovers landed on Mars in 2004, they operated primarily through careful human planning with limited autonomy. The Curiosity rover, which landed in 2012, incorporated more sophisticated autonomous navigation, but still relied on human decision-making for most activities. The most recent rover, Perseverance, which landed in 2021, represents a carefully calibrated hybrid approach. It uses machine learning for certain specific tasks, like identifying interesting geological features with its AEGES system, autonomous exploration for gathering increased science. But this AI system doesn't control critical rover functions. Instead, it makes suggestions that are verified by both onboard fault protection systems and Earth-based human operators. This approach reflects a crucial insight. Modern AI excels at specific bounded problems with clear success criteria, but remains problematic for mission-critical control systems where failures cannot be tolerated. Recent breakthrough applications of AI in space technology follow the same pattern. The MEXEC system, Mars Express Expert Command, used machine learning to optimize the complex scheduling of scientific instruments on the Mars Express orbiter, increasing scientific output by 32%. But significantly, the system recommends schedules for human approval rather than implementing them directly. Similarly, NASA's EMIT instrument on the International Space Station uses deep learning to analyze mineral compositions on Earth's surface, performing in seconds what would take human analysts weeks. But again, this AI system is analyzing data, not controlling critical spacecraft functions. The recurring pattern becomes clear. NASA doesn't use AI for autonomous control of critical systems. Instead, they use it to enhance human decision-making, optimize specific processes, and analyze complex data. The core functions of spacecraft remain governed by deterministic systems that engineers can fully understand and verify. Looking at current developments through this lens, we can see NASA's approach being adopted across industries. Self-driving car companies, after years of promising full autonomy, are increasingly focusing on driver assistance systems that follow these same principles: predictable behavior, bounded autonomy, and human-machine teaming. Similarly, in healthcare, the most successful AI implementations follow NASA's pattern. They help doctors interpret complex data and identify potential issues, but leave final decisions to human medical professionals. The future of AI in critical systems is unlikely to resemble the fully autonomous, generally intelligent systems often portrayed in media. Instead, it will likely follow the path NASA pioneered: carefully engineered systems with bounded autonomy, multiple layers of protection against failure, and thoughtful integration with human operators. For those building or investing in AI systems, the lesson is clear. Success comes not from pursuing the most advanced capabilities, but from understanding exactly how those capabilities can be reliably applied within specific contexts.